So this screencast is going to show you how to solve for combination circuits. So a combination circuit, if you remember, is when we have parallel portions of our circuit and series portions that are combined into one circuit. This makes solving the circuit a little bit trickier, but we can still do that using our Ohm's law, which is V equals IR, and Kirchhoff's voltage and current laws in different portions of our circuit. So this is the circuit that we're starting with. We have three resistors, resistor 1, 2, and 3. And we filled in the three things that we know for the resistors and the total voltage. So the first thing we want to do is try to solve for the total resistance, which is not going to be as easy as just adding two of them or using our parallel equation. We're going to have to use a combination. So first, the thing that we can see first is that R2 and R3 here are in parallel with each other. And we know this because if I am coming from the battery and my current is flowing through here, at this point, it gets to choose whether it wants to go to through R2 or through R3, and then it can go all the way back to the battery without hitting the other one. So it only has to go through one of these resistors, and that's how we know it's in parallel. So we can use the equation with these givens and unknowns, our equation of R23, which, if you remember, I talked about this. I am not using RT here because it's not the actual total resistance yet. It's only the resistance of R2 and R3 combined. So R2 and 3 is what we want to find. We need to put that, use the equation of 1 over 1 of R2 plus 1 of R3, where you can see if we plug in our values and we plug that into a calculator carefully, we will get our resistor value to be equal to 781 ohms. That's rounded. So now our second step is to combine R1 and R23, and we see that they are in series. So series resistors are really easy. All we have to do is add together R1 and then our R23, which is what we just found. So when you add our 350 ohms and 781 ohms, you'll see that the total resistance, that's going to come out to be 1,131 ohms. So now we can plug that into our data table, and you'll see right here we have the 1,131 ohms that we just found from using all the three resistors that we have. So now we can solve for the total current because we have 2 out of 3 of the things in this column. So since we have our voltage and our resistance, we can solve for this current. So we're going to use our equation of V equals IR, and since we want to solve for I, we're going to have to manipulate that equation. So don't forget, we're going to have to put the voltage on top of the resistance to solve for the current. And once we do that with our 15 volts and our 1,131 ohms, we're going to get a total current through the system of 0.013 amps. We can plug that into our data table, and the next thing we're going to have to do is a little bit tricky. So this is like what we went through in class, so make sure that you are using your Kirchhoff's laws to figure out which our next portion of our circuit we can solve for. So we're going to solve for the current through our first resistor, because if we remember, the total current is equal to the current going through each component in a series circuit because of Kirchhoff's current law. So the resistor 1 is in series with the rest of the circuit, and we can see that because if we're at the battery and we need to go through the circuit back to the battery, we have to always hit this first resistor. There's never going to be a time when we can go through this circuit and not touch that resistor, so we know it has to be in our circuit in this series. So we can say that the current going through that resistor is going to be equal to the total current of the system. So that's going to be 0.013 amps. And you can see that we can place that in our table. And now the same way that we did before with the total values, we can solve for the voltage going through resistor 1 because we have 2 out of 3 things in our column. So we'll use our 350 ohms and our 0.013 amps of current, and we can solve for that using V equals IR, plugging those values in and seeing that our voltage is going to be 4.55 volts. The next thing we want to do is solve for the voltages through our second and third resistor, and we need to make sure we think about Kirchhoff's voltage law, which is saying that the total voltage is equal to the sum of all the individual voltages in a series circuit. So we know that if we add the current, the voltage going through here and the voltage going through here, they need to be equal to that 15 volts that the battery is providing. So we can see that our voltage total is going to be equal to V1 plus V23. So I'm not going to use voltage of 2 and voltage of 3 separately. I'm going to treat them as one combined resistor. So my total voltage is 15 volts. I just found the voltage of my first resistor is 4.55 volts, and I want to find that unknown voltage through the 2 and 3. So if I find that to be 10.45 volts, now I can think about my voltage laws in a parallel circuit, because this portion of my circuit is actually parallel. So though the whole thing is going to be 10.45, we know in a parallel circuit voltages are all equal. So right away we know the voltage through the second resistor is 10.45 and the voltage through the third resistor is 10.45. So we can plug those voltages in, and then all of our hard work is done. All we have to do is solve for those two missing currents using V equals IR like we have previously. So when we're solving for the second one, we have our givens and unknowns. Our equation is V equals IR, and when it's manipulated, we have the current equals voltage over resistance, and we have our 10.45 volts we just found over those 2,200 ohms. That gives us a current of 0.0048 amps for our second resistor. And for our third, we can plug in our values. The only difference is that the resistor is 1,200 ohms now, and we use the same formula. And once we plug that in, we get 0.0087 amps. So now you can see our whole table is filled out, and we've solved for every point of the problem. But is there any way that we can check that we're right? So we know that Kirchhoff's current law is the one that states that the total current is equal to the sum of all the individual currents in a parallel circuit. So in this portion of the circuit, if I know the current through the second resistor and the current through the third resistor, then I can plug that into my formula of IT equals I2 plus 3, and I know that this current is 0.0048 amps, and the current through resistor 3 is 0.0087 amps. So I'm going to get 0.013 amps is equal to 0.0135, and we know that the only reason we're off a little bit is because we rounded.